Hello everyone, I am Saurav Mishra, a PhD student at the Artificial Intelligence and Robotics Laboratory, AIRL, Indian Institute of Science, Bangalore. My research interests include multi-label learning, continual learning, brain-inspired computing, and applications of physics-inspired machine learning. At AIRL, we also look into swarm robotics, aerial and underwater vehicles. Today, I'm going to present our recent work on physics-inspired networks with guided supermasks or PINGs. I am grateful to IEEE IJCNN for accepting our work to be presented at this venue. This presentation is structured as follows. First, we look into the motivation of the work, followed by relevant literature. Then, we discuss the proposed PINGS framework and the results of the experiments. Finally, we conclude with the key points and some directions for future research. Real-world systems involve multiple interconnected components, each governed by its own set of equations and constraints. These equations and constraints arise from physical phenomena such as fluid flow, current flow, etc., and may involve conservation laws. The slide here shows four examples. In the case of smart grids, the power produced at the generation sites has to be distributed to the consumers through distribution lines, and the remaining power needs to be stored in storage units. Each unit has its own set of laws for determining production and losses. For example, Faraday's laws and Kirchhoff's laws. Another example is drug delivery in biological systems. Drug transport and delivery in the tissues depends on a lot of factors such as the properties of blood, the nature and properties of the target tissue, the availability of free receptors and binding sites for drug molecules, etc. Thus, effective drug administration requires optimization of multiple physical phenomena happening one after the other. Similar things can be said for simulation of oil reservoirs where the oil and gas mixture has to flow through multiple layers of soil and rocks with different properties, and also for climate modeling. Accurate simulation of such systems requires solving multiple governing equations. In this work, we assume that the governing equations and the constraints are expressible as initial boundary value problems, or IBVPs in short, governed by a partial differential equation and some initial and boundary conditions. We use physics-informed neural networks, or PINs in short, for solving any given IBVP. So, the overall objective is to solve or simulate such systems with multiple components using a single pin. First, let us consider how a simple system governed by a single IBVP is simulated using pins. Pins have been popularly used in many different areas such as astronomy, fluid flows, heat flows, etc. Pins have also been used for identifying the unknown parameters in the governing equations of physical systems. Typically, pins incorporate physics into the learning through loss functions. The data loss term, or the supervised loss, ensures that the pin output matches the available sensor readings. The data loss alone is not sufficient for the network to generalize to the entire domain. Hence, a physics loss is added. The physics loss represents the residual of the governing PDE. Modern autograd engines allow computation of analytical gradients, making this a seamless process. In addition, loss functions corresponding to the initial and boundary conditions are imposed. Unlike traditional numerical solvers, pins do not require a uniform and fine grid-like representation of the domain. Pins can also generalize to unstructured domains. The pipeline is shown in the figure on the top. An example application on the spring mass damper system is shown in the figure below. This is how we solve a single system with pins. In the next few slides, we will see how multiple systems can be solved with the same pin. A naive way of solving multiple systems would be to use separate pins for each system. but it would be computationally expensive. Existing approaches in the literature have considered fine tuning and transfer learning for the same. While fine tuning and transfer learning can successfully handle systems with minor changes in initial and boundary conditions or governing equations, they may not handle systems with significantly different governing equations. For example, fine tuning or transfer learning may not be suitable to learn a wave simulation if the pin was trained originally on a heat problem. Therefore, in simulating systems like the ones we discussed, continual learning techniques are needed to tackle the resulting performance drop due to catastrophic forgetting. Recently, incremental learning with pins or I pins for short have been proposed as a means to do it. I pins use one of the oldest and most prevalent ideas in continual learning and network compression literature, which is iterative pruning and retraining. While pruning reduces unnecessary weights, retraining makes up for the performance loss. This is observed to work fine for model compression when the source and the target dataset is the same. However, in a continual learning scenario, it might suffer from significant forgetting in the earlier tasks due to the pruned away weights. In addition, this iterative process of pruning and retraining is computationally expensive. So, we need an alternative approach. In this context, subnetworks or supermasks present an alternative approach. Randomly initialized large networks contain subnetworks that can give similar performance as a trained model of the same size. Large networks have a lot of unused capacity which can be used to learn multiple tasks. The concept of supermasks utilizes this fact to train a single model on multiple tasks without altering the weights. For each task, a set of weights that give the best performance are identified and a mask is created for the task. The mask is applied during inference on the task. As the underlying weights are not modified, there is no forgetting. We use this idea to solve multiple IBVPs with the same pin. We call our method as physics informed networks with guided supermasks or pings in short. We propose three variants of pings. First, where supermasks are learned only at the input and the hidden layers, while the output layer is the same for all IBVPs. Second, pings plus output layer fine tuning. In this case, supermasks are learned at the input and the hidden layers, and there is a separate output layer for each IBVP. Finally, pings along with fine tuning at the input and the output layers, where supermasks are learned only at the hidden layers, and there is a separate input and separate output layer for each IBVP. Different IBVPs may have different numbers of dependent and independent variables, thereby requiring different input and output layers. Therefore, we have three variants of pings. For baselines, we consider fine tuning the entire pin on each consecutive or each subsequent IBVP and training a separate pin for each IBVP. We omit I pins due to their computational complexity. We consider two well-known PDEs, the heat and the wave problems, along with four different initial and boundary condition pairs for each case for our experiments. The next set of slides shows the results. Ablation studies on the wave problems are shown in this slide. The boundary conditions alternate between fixed and free ends. The initial condition for the first two cases is the string is slightly disturbed from its equilibrium position and then it is released from rest. For the last two cases, the string is given an initial velocity at its equilibrium position. The initial condition is shown as the solid black line. The dotted line is the solution computed by our algorithm, and the solid green line represents the analytical solution. Here we compare the performance between pings and its three variants. The snapshot shown in these plots is taken at 0.25 seconds. The plots show that pings with fine tuning at the input and output layers gives the best performance with the least forgetting. Forgetting is observed as mismatch between the solution computed by our algorithm and the analytical solution. As stated earlier, fine-tuning the entire network and separate pins for each IBVP are taken as baselines. In this slide, we test our algorithm, which is pings with input and output layer fine-tuning on two heat problems and two wave problems. The first two problems are heat problems and the last two are the wave problems. For the heat problems, the solution dies soon because there is no external heat source. So the snapshot shown is taken at 0 seconds. For the wave problems, the snapshot is taken at 0.25 seconds. Separate pin for each case undoubtedly gives the best performance, whereas pings with fine tuning at the input and output layers comes very close to it. The heat problem is a parabolic equation whereas the wave problem is a hyperbolic equation. This set of results shows that pings with fine tuning at the input and output layers can handle significant changes in the governing equations. Fine tuning the entire network, which is shown in the middle row, performs the worst as it incurs maximum forgetting due to continuous weight updates. In the final sequence of IBVPs, we alternate between heat and wave problems. This setting represents the maximum possible change between consecutive governing equations. Simulations show that pings with fine tuning at the input and the output layers performs the best, demonstrating its capability to handle significant changes in the governing equations. Minor forgetting issues are observed due to trainable biases present in the hidden layers. This is seen as a slight mismatch between the analytical solution and the solution computed by our method. We conclude that pings with fine tuning at the input and output layers performs the best, coming close to using separate pins on each problem, even on challenging IBVP sequences. In the future, we will include various more challenging problems. Convergence and parameter sensitivity analysis will be done in greater detail. So that's all from my side for the presentation. I hope you liked it. And thank you for your patient hearing. Have a great day. Thank you.